Okay, so when it comes to chapter 4, for the first part today, I want us to just get the idea. If you can get the idea of hypothesis testing, the rest, the technicalities sort of sort themselves out as we go. But it's the idea that is crucial. And I like, the more I think about it, I like this pot of beans example. Because this is now exactly what we're going to do. We are going to have the whole population, the whole pot of beans. And instead of eating the whole pot of beans, you are just going to take one spoonful. Taste that, and from that, infer something about the whole pot. So if your hypothesis is that the pot of beans, or all the beans in the pot are cooked correctly, let's say. That's what I want to test. I want to see if that's true. The only way to know that for sure is to eat all the beans and test every single one. But I think unless you have a huge appetite, that's not necessarily practical. So what you're going to do is you're going to get a little sample, taste that, check that, and if that sample of beans were all cooked, if all those beans were cooked correctly and they taste good, then is it reasonable to conclude that the whole pot of beans is a good one as well? Depends. Did I stir it correctly? Is my sample representative of the whole pot of beans? And that's where the issue of sampling comes in, that I have to have a sample that's representing the whole pot. If I just turn up the heat and wait and I didn't stir it at all, and I take a sample towards the edge, maybe they cook faster than the middle beans. And it's not necessarily correct to conclude that from a spoon that's full of cooked beans, that the whole pot of beans is cooked. So sampling is an issue that we sort of avoid on purpose. When you actually get to doing your own research one day perhaps, then sampling is a real issue. I have to make sure my sample is as unbiased as possible and balanced and representative of the population that I'm examining. But for now, we're going to sidestep that issue a little bit, focus on how we use the sample to make a conclusion about the population. And how we do that is by way of hypothesis testing. So I have an hypothesis, the beans are cooked well. Then I take a sample, and based on what that sample is telling me, I make a conclusion about the whole pot. That is inferential statistics by way of beans. Honestly, I wouldn't have come up with this example if it wasn't in the book. The textbook is so good. But it's such a nice example, I'm going to use it all the time now. Okay, so here is an example that's maybe a little more relevant than beans. So don't look at the rest too much, I'm just looking at the question. So I have a person, and she claims that she can identify people with above average intelligence with her eyes closed. She can just walk up to a person and pick one that has above average intelligence. Now, I'm looking at the population of all people, and I know that when it comes to their intelligence, by measuring by using the IQ scores, the average IQ score of people in my population is 100, standard deviation is 15. So now the woman's blindfolded, taken to a stadium full of people, so a very large group of people, as if it's the whole population. And she randomly selects one person, that'll be the sample, and she chooses someone with an IQ of 140. So now I look at my sample, the one that she picked. Could that have been by chance? Now, based on the distribution of the intelligence, 100 standard deviation of 15, do you think 140 is common or not common? Not common at all. We saw it to be in the 90th percentile, it's like 119 IQ. So 140 is way out there. So the question then is, did she just stumble onto a person that has that high an IQ? That person is pretty hard to find in the stadium of all people. A very small proportion of people will have that IQ or better. So could she have done that by chance, or is there then reason to believe or evidence that supports her claim that she can just pick out a person of above average intelligence? So we are stating this by using a null hypothesis and a research hypothesis. Some books also call this one the alternative hypothesis. So the research hypothesis is sort of what I want ideally. I want this to be true, but I don't know if it is. So if I look at the two, population is a bad word here, or whatever. Population 1, the people chosen by the woman, so it's just the one person. And population 2, the whole population, the general population, the people not chosen by her. So I kind of want her to be correct. What I want is the intelligence of the person she picks to be higher than the average intelligence of the whole population, which would then give evidence, or if this research hypothesis is true, then that supports her claim that she can pick someone of above average intelligence. The null hypothesis is then the opposite, that the person she picks does not have higher intelligence than the population average. So it's one of these two. One of these two is true. Either it fits with her claim that her sample, I don't know what you say sample, her pick, number 1, has an intelligence higher than the average, or it does not. So then her choice, her person's intelligence is less than or equal to the population average. Everyone with me so far? So I'm just going to use the research hypothesis and the null hypothesis to just give some structure to my investigation for her claim. Okay. And I know that the population in general behaves according to a normal distribution with mean 115. So before we go ahead, let's just think about this. So if she picks, so let me write this down a little bit. So my population has, I'm looking at IQ values, and the mean is 100, standard deviation is 15. So if she picks an IQ of, let's say, 145, how do I determine how unlikely that is? I know 145 is high, but exactly how high is high? Well, let's see, what is the corresponding z-score here? Well, it's 100 plus 15 plus another 15 plus another 15. So this one is going to be z-score of 3. It's 3 standard deviation steps away from 100. So if I have a little visualization here, That's my 0, 1, 2, 3. So my line is over here that I'm investigating. That has a probability, if I look at the table, which is on page 670 something. I'm now looking at a Z value of 3, 676 percentage in the tail, so the percentage above Z equal to 3.13. I'll leave that open. .13. So in our estimations, we don't really consider anything past 3, but there is a little bit of the population for which that can happen. 0.13%. Right? That's a very small little bit that the tail has. If she picks an IQ score of 130, I'm just picking nice numbers so we don't have to worry about getting the Z value. That would be a Z value of 2. And then that's 0, 1, 2. What is that probability? I look for 2, 2, 2, 2.28. Is that right? 2.28%. Remember, my estimate was 2%. So the exact number is 2.28. So there's only roughly a 2% chance of getting this IQ value or better. Whereas if she picked someone with an IQ of 145, there was really only a 0.13% chance of that happening, or better. So depending on what she picks, if I look at the corresponding Z value and the percentage, the probability of that actually happening, I can measure how likely it is that she just stumbled onto that person by chance, or if there is some evidence that suggests that her claim is actually true, that she can identify someone with above average intelligence. I'll do one more. If she picks an IQ of 115, that's a Z value of 1, that puts me over here, and the probability of Z equal to 1 is 15.87%. So now I think, well, yes, you did pick someone with above average intelligence. It is above average, but it's not above average by much. That you had a 15.87 chance of picking that person randomly. If I just randomly pick someone, the chance of the probability of them falling in this range is almost 16%. So that could have happened by chance. You're not necessarily showing me that your claim is true. Whereas if I randomly select a person in the stadium, the probability of me getting someone in this region, 130 IQ or above, is only 2%. So if you can do it with one person, that gives me more evidence to suspect that there's something to your claim. So it depends on what her choice is, what the sample is, and where it sits in the distribution. So I can determine in advance what percentage am I going to be happy with before I accept her claim. Am I happy with 15%? No, not really. I can do that by chance. 1 in every 6, more or less, is going to fall in this range. Am I happy with 2.28%? Well, I think so, yeah. So you decide beforehand what percentage are you happy with. The standard is sort of 5%. 5% is okay. The chances of you just randomly getting that with a 5%, if I pick 5% as my cutoff, and she goes and chooses a person, I'm happy with 5% because chances are you wouldn't have picked that randomly. So I could choose, for example, my cutoff as 5%. So I say, okay, here, there's a line here, so that the chances of picking someone in this right tail is 5%. I know that from the distribution. If you now pick someone and you get someone in there, I'll give it to you. Because it's fairly unlikely. I've decided 5% is what I call unlikely enough. If you happen to get someone in there, then there's evidence to accept the research hypothesis that the person you pick has a higher than average intelligence. And if you did it again, that it falls in there, that gives me evidence to say, no, my null hypothesis, I'm going to reject this, that because it seems as if, based on her sample of one person, her sample did fall above the population average by enough so that I say, okay, that's good enough. Does that idea make sense? Just the idea for now is what I want to focus on. So, 4.1, 4.2, no, where are we now? 4.1. Okay, so I know the distribution of the population. I determine the cutoff. For example, 5%. So the top 5%, if she picks someone in the top 5%, I'll give it to her. That's enough evidence to suggest that it wasn't by chance. So what is the z-score that corresponds to this line? What's the z-score here? Well, I simply go and look at my table. Now I'm looking for 5%. 5%. Wow, well, see, it's a little unfortunate that it sits in between. I get 5.05 at, where am I now? 1.64, and I get 4.95 at 1.65. So in this case, I'll pick this one. Because if I pick the other one, then my cutoff isn't really 5%, it's actually a little less. So I'll give her the benefit of the doubt, and I'll say, okay, I'll pick 1.64 for you. So 1.64, what IQ value does that correspond to? Well, that's going to be 1.64 times the standard deviation plus the mean. What do I get for that? Did they tell me? Oh yes, right there. 124.6. So if you pick someone that has an IQ of that 124.6 or greater, there's enough evidence to suggest that you do have the skill that you claim to have. But we decide on when we're comfortable with accepting that research hypothesis. 5%, 2%, 1%, you can decide beforehand. And of course, the smaller you make this, the less chance she has of actually giving you enough evidence. But you want to be, you want to sort of not be too extreme either. Okay, so we get our cutoff. Then we see what the sample is doing. For example, she picks a 140. Then you can say, well, 140 is above. If it falls above, then there is evidence to reject the null hypothesis, and it supports the research hypothesis. I can't say I accept the research hypothesis, even though sometimes books say that. I can only say that the evidence supports her claim. I don't know for sure that her claim is correct and that she actually has that skill. She could just be that lucky. Can't say for sure. But the evidence that she gives me with her sample, with her choice of a person, does support her claim. Does support her claim. So that's the idea of hypothesis testing. I'm trying to test a claim, a suspicion. I look at what the sample is telling me, and within some range of, let's say, acceptability, depending on where the sample sits, I either accept it as supportive evidence or I say, no, it's not good enough. Any questions on the idea of hypothesis testing? So if I visualize it again here, I say, okay, I'm going to be happy with 5%. If you pick someone in the top 5%, that's probably not by chance. So this is going to be my cutoff. Anything you give me in the sample that's higher than this, and I will see that as evidence supporting your claim, supporting the research hypothesis. Oh, that's it. So that's it. I thought there was another one. So then if you pick someone in the 140 here, and say, oh yeah, that's, I'm happy with 5%, giving you a little bit of room to move. So we reject the null hypothesis, and it supports the research hypothesis that you do have that skill. But I'll never know for sure, unless, well, if she keeps doing it, maybe. Any questions on the idea hypothesis testing? So I'm introducing the idea today so that you have time to just let it percolate. And so that tomorrow is a little bit easier. So let's look at two more examples just to drive it home, so to speak. So lottery example. Let's just erase this. Lottery example. So a study is done in which a randomly selected person is given $10 million. This person's happiness, measured 6 months later, is 80, a score of 80. So we know in advance that the happiness scores of people in the whole population has a normal distribution of 70 with a standard deviation of 10. Could this have happened? Could this happiness of 80 have occurred by chance? Or is there evidence to suspect that it's because of the $10 million? So my two populations in question, people who got $10 million 6 months ago and people who did not. So what am I hoping for? I see the research hypothesis as what I'm hoping to prove, what I'm hoping to conclude, is that this person, or in general, people will be happier with the $10 million 6 months down the line. So I'm hoping that the average happiness score of people that receive $10 million is higher than the population average. And the null hypothesis is then the opposite, that people that receive the $10 million are not, let's say, not significantly happier. On average, it's not really more. So I I know that it's a normal distribution, 70 mean and 10 standard deviation. Now I decide on my cutoff. My probability that I'm okay with is 5%. So the corresponding Z value is again 1.64, and the happiness score that's related to that will be 86.4. So in order for me to say, yes, there is evidence to suggest that those people are happier, significantly happier, I would have to get to a Z value of 1.64. It has to be within this 5%. In other words, I have to have a happiness, I have to see a happiness score of 86.4 or above. Now this person in the sample only has a happiness score of 80. So the Z score is less than 1.64. The happiness score, 80, is less than 86.4. So now I have to decide, is that enough? Is that evidence strong enough to reject the null hypothesis? And can I say, yeah, that definitely suggests that people are happier. This person is happier, but because it's not by that much, it's not that much more than the average, I can't say that there is enough, there is strong evidence to suggest that people in general are happier with the $10 million. It's not more extreme than the cutoff value. So we do not reject the null hypothesis. We can't say that we accept the null hypothesis. The evidence is just not strong enough. It might still be true, but based on my sample of a score of 80, it's just not enough to say, yes, I accept the research hypothesis that people are happier. It's just not good enough, because it could just be a randomly happy person. Anyway, the evidence isn't strong enough. So we don't reject the null hypothesis, and we say the result is inconclusive. I could take another sample, and then it could be different. Based on the sample I have, based on the evidence I have, it's just not strong enough with my 5% cutoff. It could just be a happy person. Because there's obviously, just if I randomly select people, some will be happier than others. And I'm trying to investigate if it's significantly happier if I look at this $10 million group. Any questions on the idea? So we're not worrying about calculations yet. We'll do all that tomorrow. I just want to get the process and the idea. Any questions on that? All right, one more example, stress reduction. Oh no, there's a graph first. So visualizing it helps again. Usually we're going to use 5%. But some studies use a 1%, and then I really need the evidence to be strong before I run with it. 5% is common as well. So you decide that beforehand, and if I then see in my sample something that's more extreme than that, I say, okay, that's strong enough evidence to say, yeah, there is something to this $10 million, and people are significantly happier. In the sample, it could just be from other reasons that the person's happier, not necessarily from the $10 million. All right, so let's do one more example to just verify the idea and the process of hypothesis testing by way of the stress reduction example, where we are trying to test to see if there is any significant effectiveness in stress reduction method. So we're comparing our general population, which has a stress level normally distributed with a mean of 40 and a standard deviation of 10. Now we randomly select a person to be trained in the method, and we find that that person's score is 25. So we have a sample of one person, and we're trying to compare that to see how does that compare to the distribution of our population. Is it a common value? Is it a rare value? Is it extreme enough to say that this is significant evidence to suggest that the stress reduction method is effective? So our population 1 is the people trained in the method. Population 2 is our sort of original population without any training or effect. And I'm trying to see with my research hypothesis what I'm hoping to be the case, that population 1 will have a reduced stress. So I have a less than or equal, not equal, just that the mean of population 1 with the stress reduction method is strictly less than population 2's mean, that there is an improvement. And the null hypothesis is then the opposite, that there is no improvement, it could also be worse. So greater than or equal to there. So now, what is my characteristics of my comparison distribution? What is the distribution that I can compare this sample to? The sample of 1? Well, it's a normal distribution. For people in general, have an average stress rating of 40 and a standard deviation of 10. So when I visualize what I'm going to do here, I have my normal curve, my bell curve, or some representation of it. And I'm going to look, so this is a normal curve. I have a mean of 40 and standard deviation of 10. So now I'm trying to see if I'm going to choose a significance level of 1% or 0.01 that will put me on the left here as my cutoff value, so that this area over here is 1% or 0.01, depending whichever one you want. So what is the corresponding cutoff Z score? Well, I go to my table and I see, let's do that together. I see on page, where are my tables? Starting on page 673, I'm looking for a tail of 1%. So I'm going to go down in the tail column, down until I hit 1% on my page 676, and I get 0.99, which is the closest value, which in my table is going to correspond to the right tail for a Z score of 2.33, but I'm on the left, so it's going to be negative 2.33. This I'll call my Z cutoff. So if I look at my sample and I get anything to the left of that, then I'm going to say, oh, that is pretty extreme. I'm not going to expect to get that unless there has been a change in the population due to the stress reduction method. So now I look at I can look at it from two different angles. I can look at it as, what is the corresponding raw score that corresponds to that cutoff? And I see it is a 16.7. And then I can compare my sample value, which was what? What was my sample value? It was 25. Clearly 25 is not as extreme as the 16.7 cutoff line. So I could have just gotten that without any change in the population. Another way that we usually do it is to look at the 25 score from my sample, convert that to a Z score, and I'll get, with the formula that we've seen before, I get a negative 1.5. So I'm not going to be out here in the tail just to have it more easily visible. So I'll call my Z observed to be negative 1.5. So clearly that is not past my cutoff into this extreme region where I'll say, okay, that's extreme enough. The evidence is significant to suggest that the mean has changed from population 1 to population 2, lower in fact. this is not significant enough according to my desired significance level, so I say it's not more extreme. I'm not going to reject the null hypothesis in favor of the research hypothesis. The evidence just isn't strong enough. So I'll say it's inconclusive and do not reject my null hypothesis. If I visualize this, like we have here, and it's always a good idea to draw this yourself, see all the pieces, and visualize what's happening here. It makes it so much easier. There's my cutoff, whether you look at the z-score or the corresponding raw score. We usually just look at the z-score, and then take my sample value and convert that to the z-score as well, because it's easy to look up in tables and see, is it extreme enough, is it past this cutoff in whatever direction my hypothesis test is set up. Yes it is, then I would reject. No, it's not in this case, so the evidence is inconclusive, it's not strong enough. I could have just gotten that randomly, it's not a rare enough value. I could have just gotten that without any change in the population. Okay, so we started the introduction on hypothesis testing last time to just sort of do it as early as possible, let that idea sit a little bit overnight, and making it a little bit easier today. So we had a couple of examples where, actually I like the one in the stadium, the intelligence example, where we were trying to establish if there's any evidence that supports the person's claim that she can identify an above average person without even looking at them. So what happened here, I had the population of people that she chose, which really just consisted of one person that she chose, and then the population of everyone else. And I was trying or hoping that the people that she chose has, or the people have an average intelligence mean that's higher than the population mean, and then the null hypothesis is the opposite. So what happened in that case, she essentially took a sample of one person. By choosing one person, there was a sample of one person, and I could look at the intelligence score of that person, decide on my cutoff, let's say 5%. Then if her selection, I think it was 140, was more extreme than my cutoff, then I can visualize like this. If her sample, if the sample that I got through her was in this right tail that's cut off by my 5% decision, then I could say, well, that's enough evidence to suggest that it wasn't just by chance that she got that fairly extreme sample value, and there is evidence to support the research hypothesis that she can do what she claims. Okay, so let's leave it at that for now. So I will call this this percentage that I decide on beforehand, I'll call that the confidence level or significance level, whichever one you want to say, want to use. So obviously, if I choose a smaller percentage than 5, if I choose, for example, 1%, then my cutoff is going to be further out. So the 1% or the 5% here in this diagram indicates the probability that if I choose a random person from the whole population, what is the probability that their intelligence will fall in this area on the right here? That is 5%. So if I choose a smaller significance level, like 1%, then it's going to be a smaller area here. That if I choose someone at random, the probability of getting an IQ in the top 1% is going to cover a smaller area under this normal curve. So I have a stronger requirement that she's going to have to really pick someone that's really rare before I'm happy. So the smaller the significance level, the stronger my evidence is that I require before I reject the null hypothesis and feel that it's strong enough evidence to support her claim. So we want it to be fairly unlikely that I can get a sample value like that by chance. Many people feel 5% is a realistic number. If I make it too extreme, then I'm almost never going to have strong enough evidence. If I relax it too much, if I make this too big, well then I can get sample values that just occur by chance. If I, for example, take the significance level to be 20%, then I'm covering a large area here. And just getting a sample value could just be by chance that I get someone with that high an IQ, because there are a fair number of people in this region, 20% of the population. So I don't want it to be too big, but I don't want it to be too small as well. Something in the middle, and 5% is often a good one to use, and we'll use that one very often. But some people do prefer 1%. If I have a study, and based on what I'm going to find with my hypothesis test, it's going to cause us to implement a whole nationwide project that costs a lot of money, I want to be very sure that I'm doing the right thing and that the evidence really suggests that it's worth doing. And then I might shift this a little bit to the right, depending on how costly the decision can be afterwards. So I have my significance level. So if I then find the sample value, in this case if she picks someone with an IQ that's above this cutoff value, then I'll say that the result is statistically significant at the 5% level. I can also write it as a percentage. So I'll say that it's significant at the 5% level, or we can write it as just 0.05, or because it's always going to be 0 point something, some people just write it as 0.05. Sometimes they write it as p less than 0.05, p then being the probability of choosing a random person from the population that fall in this region. And sometimes if I do a statistical test, the software can give me a lower value, showing that yes, this was my cutoff, but actually I can do even better, and I have a stronger evidence than what I initially was happy with. All right, so let's look at transparency 4.4. This was another example, the lottery example. Whoops. Where I again had a study where I wanted to see if people that won the lottery in some way 6 months later were actually happier. So I decided on my 5%, see what my sample suggests, and my sample showed someone that was happier but not extreme enough that it supports the evidence that was due to the lottery, to winning the lottery. It could just have been a randomly happier person. and there are a fair number of them here. So it's not strong enough evidence. So because I wanted to look for someone that was significantly happier than the population average, I was only going to accept or reject the null hypothesis and have evidence that supports the research hypothesis if I found someone on the right here, this extreme. If I found someone very unhappy, well, that doesn't really support what I was hoping for. So we have what is called a one-tailed test, that I'm only going to make a decision if I see a sample value that's on the right here. One-tailed test. I'm only interested in the one side of the normal curve. So look at 4.6. Here we had our stress reduction example that we talked about last time, where I wanted to see if the method that I was applying actually reduced stress significantly from the population mean. So I was looking for something, or hoping for something, that is to the left far enough from the population mean. So if someone's stress level increased, then that's not even close to evidence supporting my research hypothesis. And again, I was only interested in the one side of this, of the normal curve, and it's again a one-tailed test. One-tailed test. But sometimes, we go to the next slide set here, which is this one. Sometimes I just want to see if there is a difference in my sample, or if my sample suggests a significant difference from the population mean. I don't necessarily care if it's higher or lower. I just want to investigate if it's different. If it's different. Then, if I still use a 5% significance level, I now have to split that up into two pieces to have something that covers when my sample is far to the left, but also far to the right. So now I'm sort of dividing the 5% into 2.5% pieces to cover each side. I still want to have a significance level of 5%, so I want there to be a 5% probability that if I choose, if I take a little sample at random from the population, it has to be 5% chance that I get something far away from the mean, which means I could get it less than or greater than the mean. So then I have what's called a two-tailed test, and I have to divide my 5% by 2 to get 2.5% on the left and 2.5% on the right. So if I then use my textbook, which I can read, and I look at the table for the z-scores, I'm now going to look at the right tail having an area of 0.025, because the other half of that is in the left. So to find the z-score now, it's going to be a little higher than before, 1.96, because I sort of have to split my focus into two pieces. It could be on the left or on the right. So my z-score is going to change then. So just remember that for a two-tailed test, my significance level is divided by 2, and that half of that goes on either side of my normal curve. Two-tailed test. I'm just trying to see if something is different, significantly different from the mean. I don't know necessarily if it's going to be more or less. Yes?
Where are you getting the 1.96?
In the Z table. If you look at, you can pass me the book and I can help you look. My book is in my office. Very convenient. So now I'm looking for the two columns is going to be the percentage in the tail, and that percentage for probability is 0.025 or 2.5%. So I'm looking for a 2.5% in the right-hand column. I keep looking on page 673. 2.5% corresponds to a z-score of 1.96.
Okay, thank you.
So the table has it in percentages, but you just go back and forth. 0.025, 2.5% is the same.
Okay.
So I'm getting this value now because I'm sort of splitting up. I have to cover the possibility of it being higher or lower. So a two-tailed test. Two-tailed test. All right. So because I don't know exactly which direction it's going to be when I take my sample, I have to cover the possibility of it being extremely high or extremely low. But I still want a total of 5%. Does that make sense, sort of? So one-tailed test. If I have some information or I'm investigating something specifically like reducing stress, then I'm trying to investigate if it is significantly lower. Getting someone that has higher stress after the treatment isn't evidence that I'm looking for. So then I can have everything on one side. But if I'm looking for something that's just different from the population mean, then I have to sort of divide and conquer, so to speak. And if I have a different significance level of, let's say 1%, then I have 0.5% on the left, 0.5% on the right, and I find my z-score again using the table. So these two significance levels are the common ones, 5% and 1%, and it depends on the type of test that I can visualize. Is it either just one side, either a higher or lower side of the mean, one-tailed test, or do I have to split it up with a two-tailed test? That should be very obvious in the question. So let's look at a couple of examples. Depression example, sort of adjusted a little bit. So there's a new type of therapy to reduce depression. It could make the patient's depression better or worse. And I'm selecting incoming patients for the new therapy, and after 4 weeks the patient scores 41 on the test. And in general, for the usual therapy, the population in general has a normal distribution when it comes to the depression score, with a mean of 69.5 and a standard deviation of 14.1. So I'm comparing the sample of one person, their depression score, I'm comparing to the mean, and it could be higher or lower. I'm just investigating if there is a significant difference. So my research hypothesis in this case, I don't want to just assume anything, so I'm playing it a little bit safer and just investigating if there's evidence to suggest that it's different from the population mean. Then the null hypothesis is going to be the opposite, saying that they are equal. So I'm trying to see, is the sample value of 41 significantly different from the population mean? It's probably always going to be a little different, but is that difference significant? So I determine my cutoff, my significance level, let's say 5%. And now because I'm doing a two-tailed test, I have a top 2.5% and a bottom 2.5%, giving me the z-score of 1.96 as my critical score. So the patient score is then a 41, which corresponds to a z-score of negative 2.2, negative because it's below the mean. 2.02 and it's just past my critical score on the left. So my critical score, my cutoff is over here with 2.5% on the left. The critical score just falls under that. So I can say at the 5% level, the sample value that I got, the evidence is significant to suggest that I can reject the null hypothesis, which was up here somewhere. I can reject the null hypothesis that they're the same. The evidence suggests that they are not the same. And I can reject the null hypothesis. So it depends on what kind of test I'm doing, what I'm trying to investigate. Maybe I have to split it up in a two-tailed test, or maybe a one-tailed test is sufficient. But I always want to try and visualize what I'm trying to do here. The normal curve, one-tailed test has everything on one side, two-tailed test. If I'm using 5%, then it's 2.5% on either side. What is my critical score? What is the cutoff value? And how does my sample compare to that? So it's very similar, very similar. So there is a little bit of controversy in terms of do we do a two-tailed test or a one-tailed test? There are different opinions. But for us, luckily, the question will make it fairly clear. I would say if there's any doubt, you can start with a two-tailed test, just to see what happens first. And then maybe you can adjust it and see. The evidence suggests that the depression is always decreasing. Now let's maybe change it to a one-tailed test. So it depends on the question, it depends on what I'm investigating. There are different opinions whether to use a one-tailed test or a two-tailed test, but our questions will be fairly clear on that. Okay, so how does everyone feel about the introduction to hypothesis testing? Again, same as for the other questions with the normal curve, I want to visualize what is happening here. Visualizing it by way of something like this makes such a difference to what I'm trying to do and what do I need to do next. Okay, I have a normal curve, there's the mean, standard deviation, that gives me my z-score values for the population. Now, hypothesis test needs some cutoff value. Find the cutoff value. Now let's see what my sample is doing. Where does that sit in relation to this cutoff critical score? And then based on that, I make a decision whether the evidence is strong enough to reject the null hypothesis in favor of the research hypothesis. All right, in this example, we are going to look at the question, does pollution affect the amount of sleep that a person gets? So, a person living in a polluted region was selected randomly, and his sleep the night before was 10.2 hours. Now I want to look at the population in general. The amount of sleep is normally distributed with a mean of 8 and a standard deviation of 1. So I have two populations here. Population 1 is sort of the changed one, the one after the treatment, after the effect, after the method was applied, things like that. In this case, pollution. People who live in polluted regions will be population 1, population 2, just people in general. And I want to know, now I don't know, does pollution affect it in a negative or a positive way? So I'm not sure, should I require a less than or a greater than? To be safe, I'm just going to look at difference, good or bad. So my research hypothesis is to see if population 1's mean is different than population 2. I don't know if it's greater or less than. And the null hypothesis is then that there is no change due to pollution between the two populations. So I have a two-tailed test in this case. Now again, I'm going to look at my comparison distribution, which is a normal distribution. I have a sample of one person that I'm looking at, and I'm comparing how does that sample fit with what I would get in general in the population. Is it rare? Is it common? Does it suggest that there is a change between the two population means? So I have a normal distribution from population 2 when the null hypothesis is true. That's my comparison distribution, mean 8, standard deviation of 1. So now I'm going to visualize what is happening here and what I'm trying to do. So under the null hypothesis, I have a normal distribution. Let's say here under the null hypothesis, I have a mean of 8, standard deviation of 1 for my population in terms of number of hours slept. Now I have a two-tailed test, so I'm trying to see if there is a difference in the mean. So at a 5% significance level, I'm going to have to split that up into two tails. Each side will be 2.5%. So in total, I have 5%. Now I look what is the cutoff Z score. Well, I go to my table. Now I'm looking for the right tail of 2.5%. 2.5% I will see on page 675. And I see a 2.5 right there. It's 1.96. 1.96 and negative 1.96. So you could say here your Z cutoff is plus or minus 1.96. I'm then going to compare that to the Z score of the sample value that I get, sample score that I get, which is a 10.2. Now, that's higher than the population 2 mean, but is it significant? Is it high enough to say that that's not really something I would get randomly? So my corresponding Z score is calculated at 2.2 positive. So I will put that as a dotted line over here. 2.2 is Z observed. And then I can see, well, it does go past one of the extremes. I didn't know which one, so my hypothesis test split it into two. It does go past the positive cutoff line. So that suggests that the sample that I got was so unlikely that something would have had to have happened between population 1 and 2 to make this a more common sample value that I would get. It's so rare that I don't expect to get something like this, so that when I do, I have evidence to think that there has been a shift in the population so that I can now get these as more common values. So I can say that it's extreme, more extreme than the cutoff value at a 5% significance level for a two-tailed test. And I can reject the null hypothesis in support of the research hypothesis and conclude that there is evidence to suggest that people living in polluted regions sleep differently than people in general. So the two-tailed hypothesis test is saying whether it's different or not. If I can't necessarily be sure which way it's going to be different, I just look at the two-tail. For one tail, I would be able to say which side it actually is. If we visualize that in the slide as well, similar to what we've done, and I encourage you to do this for yourself every single time so that you can visualize it a little better. Just makes it much easier. You have your two cutoffs because I split the 5% up, giving me a Z cutoff value of plus and minus 1.96. I get my observed value and it fell over here, more extreme than one of them. so I reject.